So we've looked a little bit at the nature of electric fields, and we compared them to gravity a little bit, and the idea behind charges, and then we looked a little bit of calculator type stuff. But it's time to start. You guys start looking at some electric forces. So actually trying to find the force of charges in electric fields. Now the nice thing is this is actually very, very similar to gravity in many ways. And if you guys can calculate gravitational force, which you guys have done a lot of, it actually makes calculating electric force relatively simple. So, for example, let's just take this. You know, you've got a mass inside of a gravitational field, you know, called just G or whatever it is. And what you guys did before is, you know, you calculate the force of gravity was equal to mg. Well, the idea for electric fields is really similar. There's not much difference between the two. One of the key differences is we don't really care about a gravitational field, though. We care about an electric field. So we don't really need a gravitational field. We need an electric field. So we're going to switch this gravitational field out for an electric field. Now, the other thing that we can change is the object itself. Electric fields don't care about mass. We don't want a mass. Electric fields care about charges, little tiny q's. So we just switch out the m for q, and we do the same thing in the expression. Electric fields act on charge, not mass, and we just switch out the relevant quantities and we change it from a gravitational force formula into an electrical force formula. And that's basically it. So instead of gravitational force, now you are calculating electric force. We don't use mass, we use charge. We don't use a gravitational field, we use an electric field. So to calculate electric force on a charge is just QE. So very similar to mg, just using the different quantities that are relevant for electric fields, and that would be QE. And once you have this force, you can do the exact same types of things you guys have done before. We can use this force in order to find accelerations, which of course lead to change in v's, and which lead to distances, and all the regular stuff that you guys have done previously. So there's not much difference between the two. Once you do the initial calculation using different quantities, everything else is pretty similar. The only thing is that's kind of different is the values that you'll be using are a lot harder to relate to. It's not like the speed of a car or the acceleration of a dog or something like that. The acceleration and speeds can be a lot harder to predict and relate to because we're talking about typically subatomics and small things, which can have crazy accelerations and crazy speeds and stuff like that. So that's where it gets a little bit different. But the actual calculations and stuff that are pretty much the same type of thing. One slight difference that'll kick in for what we're doing though is when we have an electric field, and let's say we've got a proton, and this proton is in the electric field. And if we go back to what you guys did previously, we have, you know, like parallel plates and stuff like that. So maybe we'd have a couple parallel plates making that electric field. This would be the positive plate on the left side, and this would be the negative plate. And we know it's negative plate and positive plate because electric fields go from positive to negative. So this proton would go towards the right. Positives always go with the field. That's how we know what direction to draw the field. You'd be repelled by the positive plate, attracted to the negative plate. It would go towards the right. Now, if you instead had an electron in here, the electron, of course, would go the opposite way. The electron would go towards the positive plate. It would go against the field. Now, this is where little differences kick in as well. When you calculate that force in the proton, you know, you do F equals QE, you would calculate the force on it. No big deal. Okay. If you calculate the force on the electron, same thing. It'd be F equals QE. Now, the difference is when you calculate it for the proton, this force will end up being a positive force, and this force will end up being a negative force. So let's just make up numbers. Let's say the force on the proton was 5 newtons, okay? And for the electron, it was negative 5 newtons. Now, what does the positive negative actually mean? Well, it doesn't actually tell you what direction it's going. because if you reversed this entire setup, the calculation would still give you the same results. +5 for the proton, -5 for the electron. So what that little positive and negative actually tells you, there's like a little invisible positive here. That positive and negative in there, it's a little bit different. It doesn't really tell you much about which way it's actually going. It sort of tells you how the charges are moving based on the field. This little positive right here tells me that the charge is going with the electric field, and this tells me that it's going against the electric field. And that's why when I calculate this type of stuff, whether it's the forces or even the accelerations and stuff like that, I often don't like to use the positives and especially the negatives because it doesn't actually tell me which way the thing is actually going. If I've got a picture and I want to know which way it's actually going to go, I'd much rather use arrows. Okay, so for the proton, if I calculated the acceleration of that proton, it's technically a positive acceleration. But I'd much rather just draw an arrow going towards the right, telling me that it's accelerating towards the right. If I did my electron, the acceleration for that electron technically is going to be a negative acceleration, but I would much rather just draw an arrow to the left telling me that the electron's actually going towards the left. So that's where it gets a little different with this type of stuff. Some people always put the positives and negatives, especially the negatives. I would rather use arrows to tell me which way it's actually going. Because if I see negative acceleration, I often think about slowing down or going to left, and those things aren't necessarily true in the situation. This electron would be going to the left, but it would be speeding up. So I just like to use arrows to show my direction for different things rather than the positives and negatives. Okay, so we're going to practice this a little bit. Don't forget you will be using your super sheets a lot for things like charges and masses of the protons, electrons, as well as other things, as well as a bunch of prefixes. We use a lot of the prefixes for this type of stuff, the nanos, the micros, that type of stuff. So we'll be using that type of stuff as well. And that's, of course, on your super sheets, which have been posted on your class website. So you want to definitely download. You probably want to print those off and mark those off when you find them because they're going to come in handy. Okay, well, let's get rid of all this stuff and sort of show you how this works because it's not actually too bad once you get going. The calculations are very, very, very similar to what you guys have done before. In fact, they're almost perfectly identical to stuff that you guys have done before, just a different context. All right, so let's just take something really simple here. We're going to use parallel plates, and we like to use parallel plates because they give us nice, uniform, strong electric fields. We've talked about that before. So we're going to do something really simple here. And we'll say this is a positive plate. This is the negative plate, which tells me that my electric field would be going towards the right because electric fields go from positive to negative. All right, we're going to start super simple. We're just going to throw a proton in here. And I'm going to start with a proton. Of course, the proton is going to fire across towards the right. And we're going to give some values here. We'll give the electric field. Let's say we have an electric field of 7,200 newtons per coulomb. That's the unit for electric field. It actually comes from the force formula that you guys just looked at. Electric field is force divided by charge, so it's newtons divided by coulombs. And it's going to fire across the plates. And let's just start with something really simple. Let's just find the acceleration of the proton. Okay, well, first things first. We can find the force on the proton. Force is equal to QE. You have the electric field, that's the 7,200. The charge is on your super sheet. It's the charge of a proton. It's also the same as charge of an electron. It's often called the E value, and that is the charge of an electron or the charge of a proton because, of course, they have the exact same charge except one's positive and one's negative. So it's just often just called the E value. Not to be confused with the natural logarithm E in math, but it's just often just called the E value. So that's got a value of 1.6 to the negative 19 coulombs, and you'll be using that number quite a bit. So if we have that, we have the Q value of 1.6 times 10 to the negative 19. We've got the E is 7,200. We can then calculate those two things out, making sure to use your proper scientific notation in order to actually figure out what the value is going to be. So for Q, we got the 1.6 to the power of negative 19, and then just have to multiply that by the 7,200 for my electric field. and I've got a force of about 1.15 times 10 to the negative 15 newtons, which seems like a really small force, which it is, but keep in mind how unbelievably small these things are. So really tiny forces can do unbelievable things. Okay, so next let's find the acceleration. And acceleration, basic Newton's law, is just force divided by mass. The force, we just found the force. Mass of a proton, that is on your super sheet. That's like 1.67 to the negative 27. So make sure you find that in your super sheet and mark it. You'll be using that quite a bit. So we'll just take that 1.15 to the negative 15. We can divide that by the mass of a proton, which of course is really small. And we can get an acceleration of about 6.90 times 10 to the 11 meters per second squared. So really tiny force, but unbelievably small mass gives us an absolutely ridiculous acceleration, like basically 7 to the 11. So this thing, if it could, would reach the speed of light in like 1,000th of a second. It's unbelievable what kind of accelerations these things have. Okay, so it's going across in just unbelievable accelerations. So let's see what else we can find out about the proton going across. So let's say it goes across, and let's say it goes across in, let's say 4.2 microseconds. So this is where your prefixes kick in. So we got micro, which is one of the prefixes, again in your super sheet that we're going to use quite a bit. And of course, that's times 10 to the negative 6. So make sure you use your prefixes properly. And now that we have that, let's find out what speed it actually got to on the other side. Well, this is basically literally the exact same thing you guys have done before. You're looking for its change in speed. Of course, change in speed is just acceleration times time. You've got the acceleration over here. There's your time right there. Just make sure that you put the micro into scientific notation. Again, that's on your super sheet, the conversion. You should be able to find that and mark it off. And we can calculate the two things. So we've got the acceleration of that 6.9 to the 11 meters per second. Our time is 4.2 micro, or 4.2 times 10 to the negative 6. And we multiply these two things out, and you should get a speed of around 2.9 times 10 to the 6 meters per second, which is just an unbelievable speed, like 3 million meters per second in 4 millionths of a second. That's just unbelievable. So again, there's really not much difference between what you guys done previously and what we're doing now. The only difference really so far is the F equals QE. Aside from that, it's basic F equals MA, VAT. There's no real difference between the calculations. We're just incorporating different things. For example, like the prefixes, like the micro, we'll use micro and nano and that type of stuff. So you got to make sure you find that in your super sheet and get familiarized with that, as well as how to properly use your scientific calculator. Okay, so that's how you do basic calculations. We'll do some more practice of this stuff as well and try other things like electrons and protons and that type of stuff. If we even just change this question to an electron would just go the opposite way. The actual force calculation would be the same thing. You'd actually get the same force because they have the exact same charge. The difference would kick in is the acceleration. The acceleration for the electron would be way higher. The change in V would be way higher because an electron is just over 1,800 times lighter than a proton. So it would accelerate around 1,800 times faster and go have a higher speed when it hit. But the basic calculations would be the same, which we'll be doing some more practice with. Okay, so that's how you do your basic F equals QE. And again, almost all this is identical to stuff you guys have done before.